Thank you very much for this generous introduction. It's always a pleasure to be here in Waterloo. I was here the first time in '74, and I also was here 20 years ago, and I think I've been here more recently also. So I think it's appropriate to start with a Tutte polynomial. If you have a graph, then the Tutte polynomial is a polynomial of two variables. It's one of the most remarkable polynomials in combinatorics, maybe in all of mathematics. If the graph has no edges, the Tutte polynomial is 1. If the graph only consists of loops and bridges, you count the number of loops, the number of bridges. If you have I bridges and j loops, then the Tutte polynomial is just a monomial. And then if you have an edge which is neither a bridge nor a loop, then it's defined by deletion and contraction. You first delete the edge and take the Tutte polynomial, then you contract the edge and take the Tutte polynomial, and that's the polynomial. Except that it's not clear that this is a polynomial. It's not even clear that it's well defined. But it is. Let's take a few examples. If we just have one loop and two bridges, then this is a Tutte polynomial. If you have two vertices joined by two edges, you can delete one edge and then you get x. Then you contract the same edge and you get a loop, and the Tutte polynomial is y, and this is the Tutte polynomial of this particular graph. And if we have a more general graph, let's assume that the graph is connected now, then the Tutte polynomial can be written in this way. This was done by Tutte, where Tij is the number of spanning trees with certain properties. I'm not going to come into this, but the important thing is that you can express this function t. So in particular, it's well defined and it's a polynomial. Let's look at some well-known graph invariants. Tau of g, the number of spanning trees. Now the graphs are connected. And A of g, the number of acyclic orientations. C of g, the number of totally cyclic orientations. And by these things, we mean that in the acyclic case, there is no directed cycle, so a cycle of this type. And totally cyclic means the opposite. Every edge should be contained in a directed cycle. And since the graph is connected, this is the same as saying that the graph is strongly connected. Let's look again at some small examples. If you have just one edge, there are two orientations and they are both acyclic. There are no totally cyclic orientations. If there is just one loop, the number of acyclic orientations is 0, because if you give it an orientation, you already have a directed cycle. And the number of totally cyclic orientations is 2, because there are two ways of orienting a loop. You might say there is only one because the two ways are the same, but now there are two. And the reason that we say that is that we want these two numbers to be the same. And then things become very nice. First of all, it's rather easy to see that these three invariants all satisfy the deletion recursion, which the Tutte polynomial does. And this means that these three things have something in common, but they are not the same as we have seen, because they differ on small graphs, and therefore they are very much different later on also. But they have one thing in common, namely that they can all be written as the Tutte polynomial evaluated at a certain point x, y. And the only thing you have to do is to find, for example, for the number of spanning trees, you have to find an x and y such that for small graphs consisting only of loops and bridges, the number of spanning trees is counted by that particular monomial. When you have done that, you also do that for the other invariants, and then you see that each of these invariants can be written as the Tutte polynomial evaluated at some point. And here it is. So now we are looking at what some people call the Tutte plane. It's just the Euclidean plane with an x-axis and a y-axis, and we are now interested in the Tutte polynomial. So we call it the Tutte plane. And then in the point 2, 0, you have the number of acyclic orientations. If you evaluate at 1, 1, it's the number of spanning trees, and 0, 2, the number of totally cyclic orientations. You can also evaluate here and other places, and you get nice interpretations of certain things. But let's concentrate on these three numbers. That leads to a conjecture called the Marina-Welch conjecture, namely that the number of spanning trees is smaller than either the number of totally cyclic orientations or the number of acyclic orientations. And there is a stronger version due to Gordon-Royle, namely that the Tutte polynomial on this line, so this means the function we have here, is convex between 0 and 2. The last conjecture is wide open, except that my student Seung-Min Ok has proved that it's true for minimally two-connected graphs. So graphs that are two-connected but are not two-connected if you remove any edge. So a very restricted class of graphs, but at least it's a class of graph. On the Marina-Welch conjecture, there are some partial results. It's true for very sparse graphs. If the number of edges is smaller than 1.066 n, then the number of spanning trees is smaller than or equal, actually smaller than the number of acyclic orientations. If a graph is sparse, it tends to have many acyclic orientations. If a graph is dense, and by dense I don't mean very dense, just more than 4n minus 4 edges, then the number of totally cyclic orientations is bigger than the number of spanning trees. I asked Seung-Min to improve these bounds, and he did so with the first one. He pushed the 1.066 up to 1.29, so that was an improvement. But the number 4, he couldn't push it down to less than 3.58, and he could do it only for 3-edge connected graphs. So the conjecture is still open in this gap between 1.3 approximately and 4. And that class of graph includes many planar graphs, and it also includes the cubic graphs. So I would like to mention those classes. If you have a planar and connected graph, there is a nice connection between these invariants. The number of spanning trees in the original graph is the same as the number of spanning trees in the dual graph. And if you look at the number of acyclic orientations and totally cyclic orientations, well, they switch when you go from the graph to the dual graph. Here is a graph which has precisely the same number of acyclic orientations and totally cyclic orientations and number of spanning trees. It has 2n minus 2 edges. And I believe that maybe the following is true, namely that if you have more than 2 plus epsilon n edges, then the number of spanning trees is smaller than the number of totally cyclic orientations. And if the graph is sparse in this way, then the number of acyclic orientations is large. First, I thought that maybe here you could write 2n plus a constant, for example, 2n plus 100, but that's false. You need this epsilon here. So this would be a way of attacking the Marina-Welch conjecture, but there still would be a little interval around 2n. Cubic graphs are also in this interval, which I mentioned, and for cubic graphs we have this result. Now I'm assuming that the graph is simple. I'm assuming that it has no loops and multiple edges, because otherwise it would be false. For cubic simple graphs, the number of acyclic orientations is bigger than the number of spanning trees. There is a big literature on the number of spanning trees, also for cubic graphs. It's known how many there can be in a cubic graph. So all I had to prove was to find a lower bound for the number of acyclic orientations. And I found this lower bound. In a cubic 3-connected graph, the number of acyclic orientations is at least this number, so 6, square root of 6 to the power n times a constant. And this is not best possible. Maybe it can be, maybe the 6 can be improved to 7, but then it cannot be raised anymore because of these ladders. These ladders have approximately, well, they have constant times 7 to the n½ acyclic orientations. So there is also a nice open problem here. Can we replace this 6 by a 7? So here is again the Tutte plane. I have already talked about this line. Maybe the Tutte polynomial is convex here, we don't know. If you look at the Tutte polynomial on the negative x-axis, then you count colorings. And if you look at the y-axis, the negative part of the y-axis, you count the number of flows, the number of nowhere zero flows. And there are some numbers which are of special interest, for example, in this point, that counts the number of nowhere zero 3 flows, which I'll come back to, and down here, the nowhere zero 5 flows. Then here we count the number of 4 colorings. That's of interest in connection with the 4-color theorem. And then there is a number very close to 4 where also something interesting happens. There was a nice theorem of Tutte, and I'm coming back to that. Let me first mention the chromatic polynomial. So here is the chromatic polynomial. You have a graph, and you have a natural number k, and we look at the number of vertex colorings using colors 1, 2, up to k. And it should be so that neighbors always have different colors. That's the rule. And if you permute colors, we will think of those as different colorings, although in some sense it's the same coloring, but now they are different. The flow polynomial, well, here you put a direction on every edge, and you give every edge a number, and it should be one of these numbers, and then you want at every vertex the inflow to be equal to the outflow. The number of ways that can be done, well, that's the flow polynomial. And these two functions, they satisfy some recursion. It's not exactly the same recursion as for the Tutte polynomial, because there are some negative terms here if you try to do it in the same way as in the Tutte polynomial. But you can adjust this in such a way that you can write the chromatic polynomial as the Tutte polynomial, where y is equal to 0. You need plus minus 1 here, where n is the number of vertices, and you can do something similar for the flow polynomial. The Tutte polynomial, now let's assume that we have a 2-connected graph. Let's assume that it has an even number of vertices, just for simplicity. Then, and let's call the parameter t, the number of colorings, that's now t instead of k as it was before. If t is negative, then the chromatic polynomial is positive. Between 0 and 1, the chromatic polynomial is negative, and then above 1, it becomes positive. And now an interesting question arises: how soon can it go down and become 0? And the answer to that turns out to be 32/27. Not exactly 32/27, but it will happen above 32/27. This is a remarkable theorem of Bill Jackson. So another way of formulating this is to say that the interval between 1 and 32/27 is zero-free. It has no zeros of any chromatic polynomials. The interval from 0 to 1 is also such an interval, but that was rather trivial, and similarly 0 to minus infinity, and that's rather trivial. But this interval, that's an interesting interval, and this was not so trivial. And you could ask, are there other such intervals, or have I explained all such intervals? And there are no other intervals. I proved in 97, and I actually talked about this here in Waterloo 20 years ago. This must have been at Tutte's 80th birthday. And I don't think many of you were present at that. Maybe Murty was present. There are no other zero-free intervals. If you take any interval in this big interval, then inside that interval you will find a chromatic root of some graph. For planar graphs, I could do by the same construction that the interval from 32/27 up to 3, we have density there. The chromatic roots of the planar graphs are dense in that interval. Are there other such intervals? Well, in the interval from 5 to infinity, there are no roots. This was a theorem by Birkhoff and Lewis. They raised the question, what about the interval between 4 and 5? That question was raised over 70 years ago, and we know absolutely nothing about this interval. Well, we know something. We know that at 5, the chromatic polynomial is positive. That's the 5-color theorem. At 4, it's positive. That's the 4-color theorem. But we don't know any root between 4 and 5. I could do up to 5 20 years ago, but now we have recent progress in the interval between 3 and 4, which I would like to talk about. So I would like to call a real number good if it has the property that for every planar graph, the chromatic polynomial at that point is positive. So that's what I now call a good number. And if you look at just these two planar graphs, so here we have a triangle, and the chromatic polynomial of the triangle is easy to find because you have t. If you can use t colors, you have t possibilities for the first vertex, that's that t, t minus 1 for the second, and t minus 2 for the third. So it's easy to compute the chromatic polynomial of the triangle, and the same for k4. And if you compare these two and you want to find good numbers, you see that a good number must be greater than 3. So again, the 5-color theorem says that t is a good number for every natural number t greater than or equal to 5. This is an immediate consequence of the 5-color theorem. And then Birkhoff and Lewis, as I have already mentioned, extended this to all real numbers greater than or equal to 3. So we only have an interesting thing about 3 and 5. And I should say I'm only talking about planar graphs now. So here is again the Birkhoff-Lewis conjecture saying that every number greater than or equal to 4 is good. The 4-color theorem says that 4 is good. And then here is a theorem which I learned when I was a graduate student here in Waterloo, a remarkable theorem saying that tau plus 2, so this was before the 4-color theorem was proved, tau plus 2 is a good number. Tau is the golden ratio, and tau plus 2 is the number I have expressed here, and that's 3.618, etc. And the interesting thing, one interesting thing is that this number is not too far away from 4. So one could ask the question, will the chromatic polynomial always increase from that number? I mean, that would not be a completely silly statement. Unfortunately, that's not true, and that was known already in those days. It is possible that, I mean, here the chromatic polynomial is positive, but then there are examples where it goes down below the x-axis and comes up again at 4. So there are bad numbers between tau plus 2 and 4. But now we can ask the question, is there something special about this tau plus 2? Are there other good numbers between 3 and 4? And recently, my student Tom Parent and I proved that if you have a good number between 3 and 4, then it must be between 3.6 and 3.7. And this means it must be close to the golden ratio plus 2. And this interval, I've just been very cautious here. The gap we have is actually much, much smaller. We also have a density theorem, namely that the chromatic roots of planar graphs are dense in this interval from 32/27 up to 3.6. Remember, there are no chromatic roots below this number, but between 32/27 and 3.6, we have density for planar graphs. And then again, we have density between 3.7 and 4. And then above 4, we have the things I referred to. Between 4 and 5, we know absolutely nothing. Above 5, we know everything. The proof of this uses a result of Gordon-Royle, which I would like to mention, namely that there exists an infinite sequence of chromatic roots of planar graphs converging to 4. That was an open problem for many years. So we used this result. That was very useful for us. And then we got the following general thing. Suppose you have a minor closed class of graphs. So a class of graphs with the property that if you take a graph and delete edges and contract edges, you still have a graph in the class. You could think of it as, for example, planar graphs or graphs drawn on the torus. Let's say that forb F is the minor minimal graphs that are not in F. So if we are looking at planar graphs, that would be the two Kuratowski graphs, the two forbidden minors for planarity. For every such class of graphs, this set forb F, the minimal forbidden subgraphs, that's a finite set by the Robertson-Seymour theory. Parrot and I proved the following theorem. Suppose that we have a class of graphs which is closed under minors, such that all the minimal forbidden minors are 3 connected, as for planar graphs, for example. Then let's assume we have a graph in the class such that the chromatic polynomial at some point t is negative. Then we could prove that the chromatic roots of the graphs in F are dense in some interval around t. So that's the key result in all this. I have already mentioned this example, the planar graphs, where we have these forbidden subgraphs. We could also look at the graphs drawn on the torus or any other surface. But here we cannot apply this because the minimal forbidden graphs unfortunately contain graphs that are not 3 connected. So we can't use it there. But all the questions I raised can of course also be raised for the graphs on the torus, except we can't use what we proved. Here is a class of graphs where things work nicely. Let's look at the graphs having no K33 minor. They are very closely related to the planar graphs. But they have the property that the minimal forbidden graphs are, of course, K33. That's how we defined it. And there we can prove the following. We don't have now a problem with tau plus 2 as we do for planar graphs. The good numbers are precisely the numbers between 4 and infinity, and the closure of the chromatic roots form the interval between 32/27 up to 4, so we have a complete answer. But under the assumption that the Birkhoff-Lewis conjecture is true, that was the conjecture saying that for planar graphs, you have no roots between 4 and 5. If there are roots here, that will mess up things. But if that conjecture is true, and it has been open for over 70 years, then we have this nice characterization. Another interesting class of graphs are those having no K5 minor. And the minimal forbidden subgraphs are, of course, K5 by definition. Again, the good numbers and the closure of the chromatic roots are precisely the same as for planar graphs. So again, a clean statement. Let's also just look at the graphs on the torus. We can't use what I proved because the minimal forbidden minors contain even disconnected graphs. But we can nevertheless find the good numbers. They are precisely the numbers between 6 and infinity. And the known intervals in which the chromatic roots are dense are precisely the same as those intervals we know for planar graphs. And we conjecture that there are no others. So we conjecture that the torus looks very much like planar graphs in this respect. Let me mention some other density results. Here is a famous result of Sokal. Now we look at the chromatic polynomial as a complex function. And the complex chromatic roots form a set which is dense in the whole complex plane except a sphere, where we don't know what the situation is. For the Tutte polynomial, Jackson and Sokal found a zero-free domain. Well, when I say zero-free, it's a little misleading, but it's almost zero-free. Not for the Tutte polynomial, but they decided to work on this polynomial, which is the Tutte polynomial with some other variables. It's called the multivariate Tutte polynomial. So we have a change of variables. So they found such a zero-free domain, and they conjectured that we have density outside. And that was recently proved by my students, Seung-Min Ok and Tom Parrott. And let me just explain by a figure what the result says. So first what Sokal and Jackson proved. They proved that up here, so here you have the q-axis, here you have the v-axis. Up here, there are no roots essentially for the multivariate Tutte polynomial. Here, there are no roots, and then they conjectured density of roots outside. And in the green area, Parrott and Ok proved that, yes, the zeros are dense here. And then there was a little angle here where they couldn't decide. And if their methods should prove density here, then they would need a lot of zeros of the flow polynomial. And we don't believe that there are too many zeros of the flow polynomial, so they can't get any further with their method. So let me now look at another specialization of the Tutte polynomial, namely the flows. The five-flow conjecture from around 1970 says that if you have a two-edge connected graph, then you can put a direction on every edge, and you can also put a number 1, 2, 3, 4, such that at every vertex the inflow equals the outflow. And there are examples showing that you cannot get rid of this 4, so it's best possible. Now the first breakthrough was Gégère's result that you can do it with the numbers up to 7, so that's called a nowhere 0, 8 flow. And then Seymour improved that by 2 steps, and he came very close to the 5-flow conjecture, so this is Seymour's nowhere 0, 6-flow theorem. Here are some equivalent versions of the 5-flow conjecture, namely that every two-edge connected graph has a nowhere 0 set 5 flow. So again, you use these numbers, but now the inflow and the outflow should just be the same modular 5. So it sounds like a weaker thing, but it's equivalent with the 5-flow conjecture. And this becomes a theorem if set 5 is replaced by set 6 or set 7, in fact, by any abelian group with at least 6 elements. The 3-flow conjecture. Now in the 5-flow conjecture, we looked at two-edge connected graphs. Now we look at 4-edge connected graphs. And then the conjecture says that now you only need the flow values 1 and 2. So that's a nowhere 0, 3 flow. We say 3 because we use all the numbers up to 3, but not 3 itself. Equivalently, every 4-edge connected graph has a nowhere 0 set 3 flow. So it's enough that the inflow and the outflow are equal modular 3. And again, an equivalent version, every 4-edge connected graph has an orientation which is balanced modular 3. I call this a Tutte orientation. Balanced modular 3 means that if you look at, so you don't have flow values now, you just have orientations. And at every vertex you look at the number of out edges, the number of in edges. Those two numbers should be the same modular 3. So for example, here you have 1 out and 4 in, and 1 and 4 are the same modular 3. It turns out that it doesn't matter if we say 4-edge connected or 5-edge connected. So if you can prove it for 5-edge connected graphs, it will also be true for 4-edge connected graphs. A more general conjecture by Gégère. So instead of modular 3, we will now work modular k. Suppose that k is an odd natural number, and suppose the graph is 2k minus 2edge connected, then there is an orientation such that every vertex is balanced modular 3. The inflow equals the number of incoming edges equals the number of outgoing edges modular k. For k equal to 3, that's a 3-flow conjecture, because if you put k equal to 3 up here, you get 4. If you put k equal to 5, then up here you get 8. But that will prove the 5-flow conjecture. This was observed by Gégère. This is not completely trivial. Well, when you see the proof, it becomes trivial. But so let me point out why an 8-edge connected graph, if it always can be made balanced modular 5, then the 5-flow conjecture will follow. Let me point out how Gégère proved this. If you want to prove the 5-flow conjecture, it's sufficient to do it for cubic 3-connected graphs. That's an easy reduction. So let's try to look at a cubic 3-connected graph. Let us assume that this conjecture of Gégère is true for k equal to 5. So that was a modular 5 thing. Then we look at our cubic 3-connected graph, and we would like to find a nowhere 0 5 flow. Chaucher did the following. He replaced every edge by 3 edges. And then if you have a 3 connected graph, the new graph will be 9 edge connected. Then he used Chaucher's conjecture for that graph. That gives you an orientation such that at every vertex the incoming number of edges equals the outgoing number of edges modulo 5. Let's go back to the original graph in the following way. If, for example, you have 2 edges going up and 1 going down, then you put an arrow up and you put the number 1 there. You have 3 edges going the same direction, so down here, choose that direction and put the number 3 there. And then you see that if this is balanced modulo k, then this is balanced modulo k. And I only use flow values 1, 2, 3, 4. In fact, only 1 and 3. So that's the 5-flow conjecture, coming from this more general conjecture of Chaucher, which is sometimes called the circular flow conjecture. Now, Janos Barrett and I observed that there is a connection between flows and orientations and decompositions. I mean, I have already talked about flows and orientations, but we could find a connection to decompositions, namely the following. This was in 2005. We proved that Tutte's 3-flow conjecture, saying that every 4-edge connected graph has a Tutte orientation, an orientation where in degree, out degree are the same modulo 3. If that is true, then every 10-edge connected graph has a claw decomposition. And by a claw is the following graph, just 3 edges going to the same vertex. And when I say every 10-edge connected graph, I mean every 10-edge connected graph whose number of edges is divisible by 3, because otherwise you can't decompose into claws. And then we could prove that if we assume this result, then we don't get Tutte's 3-flow conjecture, but we get the so-called weak 3-flow conjecture, saying the same thing, except that we replace the number 4 here by a larger number. We could show that the number 14 would work. Every 14-edge connected graph would have a Tutte orientation. And not only a Tutte orientation, but all generalized Tutte orientations, which means that you can start by prescribing all the out degrees. You prescribed the out degrees modulo 3, and then you can find an orientation with those prescribed out degrees, provided the edge connectivity is sufficiently large. And that made us make the following general conjecture. Why should the claw be something special here? We conjectured that for every tree T, there exists a constant, so that every CT edge-connected graph, whose number of edges is divisible by the number of edges in the tree, that graph can be decomposed into copies of T. Let's look at some examples. For example, if the tree is just an edge, there's no problem. Clearly, a graph is the union of its edges. Look at the path of length 2. That's also easy. That's an easy exercise to prove that if you have a graph, connected graph, whose number of, so edge connectivity 1 is sufficient here. If you have a connected graph whose number of edges is even, then you can decompose into copies of path of length 2. Just an easy exercise. Then let's go to the next one, the claw. Well, that becomes equivalent to the weak 3-flow conjecture. So that was much more difficult. Instead of looking at the claw, I then thought of why not continue with the paths. And I proved the conjecture. The first path I did it for was the path of length 4. But unfortunately, I needed a ridiculous edge connectivity. Then the same year, I could do it also for the path of length 3, and I became very optimistic because now I could do it with a much lower edge connectivity. And also, I thought the path of length 3 should have the same level of difficulty as the claw. After all, there are 3 edges, and why should one be more difficult than the other? Then I went on to the paths, all paths of length whose length is a power of 2. After that, the first one I couldn't do was the path with 5 edges. That was done by my student Martin Merker. And then a Brazilian group got it for all paths. And the same year, it was done by a French group, Bench Mail, a person I cannot pronounce, Le, Stefan Thomassen. They did it also, and there's an interesting detail of their proof, namely that they can do it for 24 edge-connected graphs, regardless of which path we try to decompose into. But then they have to assume something, namely that the minimum degree is large. But they could do with essentially large minimum degree, which is stronger. And this phenomenon seems only to hold for paths, not for trees in general. Now, then I got the weak three-flow conjecture. I got it for edge connectivity 8. If you have an 8-edge connected graph, it has all generalized Tutte orientations. And modulo k, I could prove it for graphs whose edge connectivity is 100k square. And then these numbers were lowered by Lovers, myself, Wu, and Xiang. The 8 was lowered to 6, and the quadratic function was lowered to a linear function. And that's not too far from the best possible, which is 2k minus 2. But there still is a significant gap. And if, for example, k equal to 5, we can lower this to, we don't have to lower it all the way down to this, but if we just lower it to 9, we would have the 5-flow conjecture. So for 5, this is obviously 12, and if we can lower 12 to 9, we would have the 5-flow conjecture. And then applications to graph decomposition. First, Merker used this general theorem on modulo k to prove that whenever you have a tree T, you can find a number Ct such that every Ct edge-connected graph can be edge decomposed into homomorphic copies of T. So it's not copies of T, it's a little weaker. It's homomorphic copies of T. This means you take T and then you identify certain vertices. So a path, for example, becomes a walk when you identify certain vertices. And then Ben's Mail, the person I cannot pronounce, Le, Merker and Stefan Thomassen used this result and some probabilistic methods to prove the tree decomposition in general. So the conjecture is now a theorem. Now there are some interesting questions of how low the edge connectivity could be. We have the following conjecture that every 5-edge connected graph, whose number of edges is divisible by 3, has a claw decomposition. And that would be best possible. 4-edge connected is not enough for that. Remember in Tutte's 3-flow conjecture, that was for 4-edge connected graphs. But for claw decompositions, you need more. We have it for 6, and we believe that it's true for 5. So 4-edge connected is not sufficient, not even for 4 regular planar graphs, as proved by Lai. His examples look a little bit like this, so not too complicated. I conjecture that every 3-edge connected graph has a decomposition into path of length 3. That would be best possible for graphs in general. But for planar graphs, there is an old open problem by Jünger, Reinl, and Pulleblanc that 2-edge connected is enough. So that's a beautiful conjecture, and it's surprising that this has been open for so many years. So again, the conjecture says you take a 2-connected planar graph, then the edges can be decomposed into path of length 3. I should say here, we have to allow a triangle to be a path of length 3 for this to work. If you don't want that, you should say every 2-edge connected triangle-free planar graph. And the number 2 here, it's important that we have planar graphs. Here we have an example of a 2-edge connected graph which is non-planar and which has no edge decomposition into path of length 3. All this can also be related to another famous theorem of Tutte, namely Tutte's one-factor theorem. Well, there is Tutte's one-factor theorem. He later generalized it to the F-factor theorem, and Lovers generalized it to a GF factor theorem, and I'll explain what it is. So let me say what the GF factor theorem says. We have a graph, and for every vertex V, we have two numbers, GV, FV, so that's what this G and F refers to. Then we want to find a subgraph, such that every vertex in that subgraph has a degree between these two numbers. And Lovas found a structural characterization and a good algorithm for solving this problem. And if f and g are the same, then we get Tutte's F factor theorem, and if all the f values are 1, we get the 1 factor theorem. It's important that we want degrees which lie in an interval, the interval between g and gv and fv. Because if we, for example, insist that all degrees should be 2 particular numbers, for example, 0 and 3, then the problem is hard. It's NP-complete. And there was a nice open problem on that many years ago. When I was a student, this conjecture was famous, the Bestower Conjecture, and it was proved in '82 by Taskinov, also by some Chinese. The conjecture says the following: you take a 4 regular, simple graphs. 4 regular means all vertices have degree 4. Then it contains a 3 regular subgraph. At that time, it was probably the simplest open problem in mathematics, because in order to understand the problem, you just need to know what is a graph, what is a subgraph, and then you should be able to count to 4. So nothing can be simpler. But then it was proved, and around the same time, Allen, Friedland, and Calais got a very nice result, which was very closely related to that. They looked at graphs with n vertices and more than 2 n edges. So a 4 regular graph has precisely 2 n edges. They looked at graphs with more than 2 n edges. And then they proved that in such a graph, you can always find a subgraph whose degrees are divisible by 3. And then you should add that they are not all 0. So this, if you have a graph whose degrees are 3, 4, and 5, so for example, if you take a 4 regular graph and you just add an edge, then you can find such a graph, and that'll be a 3 regular subgraph. And an interesting thing about this result by Allen, Friedland, and Calais is that they could prove it for graphs where you allow multiple edges. This is not the case in the Bestower conjecture, because this graph here would be a counterexample. Now, I would like to look at factors, subgraphs with prescribed degrees, but now modulo k. And we get the following theorem. If you take a 3k minus 3 edge connected graph, and now it should be bipartite, the bipartition is called A and B. Now let us assume that for every vertex we have a natural number, d of I, satisfying some condition. Then we can find a subgraph such that all vertices in that subgraph have the prescribed degrees. So that's a factor, but I should add modulo k. So this is a much weaker condition than in Tutte's theorem, but of course we only get it modulo k. And the condition we have to add is one that has to be added, because if you have a bipartite graph and you count the degrees from the left side and you count the degrees from the right side, you should get the same, of course. And this means that these prescribed degrees added up in k should be the same as the prescribed degrees added up in b, but it should only happen modulo k. So this is a little difficult to apply to non-planar graphs, because this condition must be satisfied. So if the graph is bipartite to begin with and it doesn't satisfy this condition, then there's no way that you can do this. So it's a little difficult to apply to non-planar graphs. Here is the proof. Maybe I shouldn't say too much about the proof. So we use orientations, you see, out degrees modulo k. So we use this theorem about prescribed out degrees modulo k. I'll say no more about the proof. But let me mention a corollary, which is maybe a little pretty. If you have a graph G which is 12k minus 15 edge connected, and the number of vertices is even, then you can find a subgraph such that every vertex in this subgraph has degree k modulo 2k. And that's really a factor because now you can't have degree 0. I mean, 0 is not k modulo 2k. And the proof comes from the previous theorem in a very simple way, although the previous theorem was for bipartite graphs. This is for general graphs, not bipartite. But we can use bipartite graphs in the following way. Let's take our graph with this high edge connectivity and let's look at a bipartition such that you have as many edges as possible between the two bipartite sets. Then, of course, the graph we are looking at is bipartite by definition, but one can also prove that the edge connectivity of that graph is not as big as the edge connectivity of the original graph, because after all, we are taking a subgraph, but it is at least half as big. And that's enough for using the previous theorem. And using the previous theorem, you get this subgraph. You have to check a condition, namely that if you take the prescribed numbers, which are all k, and sum them up in A, you should get the same as if you sum them up in B. But that follows from the assumption that the number of vertices is even. And if we put k equal to 3, we get the following. If G is 21 edge connected and it has an even number of vertices, then we can find a spanning subgraph such that all vertices have degree congruent to 3 modulo 6. In particular, they are all divisible by 3, and they are all different from 0. So this looks more like a factor than the result by Allen, Friedland, and Kallai. But the penalty I have to pay is that I need this edge connectivity where they only say you must have many edges. Let me finally apply this to the so-called 1, 2, 3 conjecture by Karonsky, Lutzak, and Andrew Thomassen. The conjecture is not very old, but it has become popular. It says the following. Take a connected graph which is not just the graph on 2 vertices. Then you can give every edge a weight in 1 using 1, 2, and 3, such that the weighted degrees form a proper vertex coloring. What this means is that if you take 2 neighboring vertices and count the weights of the vertices, they should be different. And by the weight of a vertex, I mean the sum of weights of the edges going into the vertex. 1 and 2 are not sufficient, and that's easy to see. You can just take a complete graph and try to do it on the complete graph, and you'll see you get into trouble with these 2 weights only. And in fact, for a general graph, it's NP-complete to decide if you can do just with weights 1 and 2. But we have the following theorem, that weights and 2 are indeed sufficient, provided the graph has a high edge connectivity compared to the chromatic number. A somewhat strange condition. Here is a more precise version of the theorem. And I'll now assume that the chromatic number is at least 5. We have a theorem for every chromatic number, but let's just assume that now the chromatic number is at least 5. Then the theorem says the following. Let k be the odd number with the property that the chromatic number is either k or k minus 1. So if the chromatic number is 8, then this k would be 9. Let us assume that the graph is 3k edge connected, and let us consider any proper coloring, any proper k vertex coloring. So you color the vertices with colors 1, 2, 3 up to k, and neighbors should have different colors. And such a coloring exists because of the way we defined k. Then we can give the edges weights 1 or 2, such that for every vertex, if you look at the weighted degree modulo k, you get the original color. So this is a strong version of the 1, 2, 3 conjecture. Just using 1 and 2, and the coloring we get, we can actually get any prescribed coloring. So I have indicated the proof here, but I think I have used my time. So I think I'll stop here. Thank you very much.
I have a small question. So made some observations about Varaha numbers, the roots of chromatic polynomials.
Yes.
And I was wondering if maybe this notion of your notion of sort of good and bad numbers might be some other way to look at some properties that might, maybe there is some other interesting phenomena going on with the chromatic polynomials.
Yes, the Varaha numbers were certainly very interesting. And there was a conjecture, but recently Gordon Royle disproved that conjecture. I think it was the 10th Varaha number where the conjecture failed. I must say I've forgotten what the conjecture was. But there was an interesting conjecture on Varaha numbers, which seemed very strange. But now it has been disproved, so maybe we shouldn't try to remember it.
Any other questions? No, please join me in thanking Carsten again.